Lesson 8, conservative plate margins. The last of the plate margins. Just to remind you, so far we've gone through constructive, destructive, we've talked about collision zones as well, which strictly speaking isn't on the spec, but I think at A level you should know about that. There are landforms there. And now moving on to the conservative plate margins. Again, lower down the years, you may have been taught this like one version of this, but let's have a look on the spec first. So there's the reference to conservative plate margins that you need to be aware of. We'll identify some forms, but I would say the reference to this is more about the cause of earthquakes than anything. Okay. Now, as an overview, and I will repeat this when I do the section on seismicity earthquakes, you get earthquakes at all plate boundaries, right? So you can never hear that too much. The two that you get the strongest magnitudes are the destructive and the conservative boundaries that you're looking at today. This won't be that long of a video, to be fair. So this will be completing this section, and then that leaves us with another short video, which will be the next lesson, where we'll look at hotspots, magma plumes, linking to the plate movements, and how this is an additional theory which explains some of the landforms that we get that can't be explained by the conventional theory. So just let your eyes accommodate to this. So you can see we've got two cross-section diagrams here and two different situations. The key movement here is they're moving side by side. So it's not really magmatic. And what I mean by that is we're not talking about an upwelling of magma coming up. The only situation that would probably arise if there was also a hotspot in the area, which we talk about next lesson. So in this one on the left hand side here, we have the plates actually moving in different directions. Okay, that is the situation where the Haiti earthquake of 2010 and the complex geology plate system that you have in New Zealand as well. They're moving in side by side directions, opposite directions. In this situation, some of you might recognize this, even though it's a cartoon style picture. This is off the coast of the United States of America. And in this one, they're both moving in the same direction. But this plate, which is actually the Pacific plate, is moving faster than the North American plate. So we get this differential movement. I'll show this one in the next slide. So the key thing here is there is side-by-side movement, and the fundamentals of earthquakes apply here as they do to destructive margins, where you've got convection currents moving the plates. The two plates move side by side. There is tremendous friction that causes the plates to lock in place. Tremendous amounts of tension build. At some point, there's a sudden, either you could use different sorts of words, jolt, slip, break at a certain point, and you have stored energy released in seismic waves. It's not a uniform break. It could be at different points as we go down through the crust, but usually they're quite close to the surface, within between 5 and 15 kilometers of the surface, and we call those shallow focus earthquakes. And as I said, I will do more stuff on that, on earthquakes in the seismicity section. So here what we've got here is just, again, just putting that into words. Let's just double check a few things here. So either they move past each other in different directions, and if one is moving faster than the other, effectively it creates a difference where you get that friction, that stip, like nature. And remember, we're talking on a scale that's unimaginably heavy and large. And it creates a fault line, which you can see a famous example here. This is the San Andreas fault line. At this boundary, you don't just get one single line. That said, something like the San Andreas fault line is about 1,200 kilometers long. And on the next slide, you'll see the reference, more specific reference to that example. So if we look here, this example, the Pacific plate is moving at 6 centimeters a year, and the North American plate is moving at a much slower rate of 1 centimeter per year. So again, that builds that pressure up and it snaps at the focus. Loads of seismic energy is given out, hence the earthquake. And this is just one line. This makes it look really simple. On the next slide, you'll see much more complexity. There are other fault lines that kind of run parallel to this as well. So it's not just a clear-cut divide, okay? And that also makes it incredibly difficult to monitor and predict. Again, something else that you talk about. And here's the San Andreas fault line. I say that lots of films have been based on it. It's world famous, but you can also see there are some other fault lines as well. So geographers, geologists, seismologists, people living in California, etc. They're well aware of these fault lines, and if you live near one, you're certainly aware of the potential threats to you. Now, again, I've provided a template, which I suggest that you fill in some of this stuff. This is, I mean, you're probably going to put like your cross-section diagram here labeled. You could, to be fair, because it's not huge amounts of detail, probably put all of it on one slide, and you'd put maybe where both plates are moving in the same direction, that side, and opposite directions, that side. You put some locations down, and you've got the fundamental explanation that you can put there with a few specifics. So I suggest that you do that, and then you can add that to your file of plate boundary types. Okay, so that's basically it. And so the next lesson, what I'll do is I'll go on to hotspots. Thank you very much for listening. See you soon.